All right, so in this example, we're actually going to change gears just a little bit. I'm still going to be looking at answering this question about where is a function increasing, where is it decreasing, use that information to actually identify some local maxes and mins, and then ultimately look for this kind of question about where is this function going to have a point of inflection, as well as where is it going to be concave up as well as concave down. In this case, what I'm doing is I'm not giving you a nice function f of x. I don't have f of x equals blah, 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 blah. What I'm giving you actually is going to be a graph of some function, but the function that we're actually given is going to be the graph of a derivative of some function f. And that's a very important but very subtle change that happens in this situation. What I'm doing is I'm not giving you just the function f, I'm giving you the derivative, and I have to use that information to actually answer questions about my initial function. So that's kind of what's going on in this case, is that I still have to answer all of those same questions, but the way that I'm going to go about them is going to be a little bit different. Well, if you think about those first two questions about looking for where this function is increasing and decreasing, as well as identifying local maxes and mins, we know that all of these questions are going to be wrapped up with information about my first derivative. Well, in this case, I already have my first derivative. It's just given to me via a graph. So what I want to do is I still want to identify critical points. I want to test those critical points, kind of look at a few points to the left and to the right, see where this thing's going to be increasing or decreasing, and then identify if it's switching from increasing to decreasing, I'm going to have a max, and if it's going from decreasing to increasing, I actually am going to have a min. So in this case, I know that critical points occur when my first derivative is going to be 0 or my first derivative doesn't exist. Well, in this case, you can see that I'm going to have a 0 at 2. I'm going to have a 0 at 4, I'm going to have a 0 at 8, and I have actually a point where my first derivative does not exist at 6. So in this case, my critical points are 2, they are 4, they are 6, and they are 8. So I have 4 little critical points in this case. So notice that this is my derivative graph. So I am honestly just picking out the zeros of this thing. It might be tempting to look at this thing and say, oh, I have a 0 derivative at 3. But in this case, that's going to come into play when we're starting to look for points of inflection. So just kind of hold that kind of knowledge of, it looks like there's a horizontal tangent line at 3, but that's going to be connected to the second derivative. So kind of just push that in the back of your mind for a little bit. We're just looking at where this first derivative is 0 or that first derivative doesn't exist. Well, just like earlier, what I'm going to do is I'm going to grab some test points around all these critical points. In this case, a point to the left of 2. Let's just choose maybe a 1. Well, I want to know what is my function or what is my derivative going to take at 1. In this case, what I want to do is I want to find f prime of 1. Well, f prime of 1 is just simply obtained by looking at this graph, go to 1, go up to my y value, which in this case is going to be a 2. So you can see that at 1, my derivative is equal to 2, which is going to say that I'm going to be positive. I'm going to have these positive derivatives kind of to the left of 2. Another point that I could grab would be, let's say, at 3. 3 is a nice point between 2 and 4. If you go down to the y value there, you see that my derivative is going to be negative 1, which is going to say that my derivative is negative between 2 and 4. Likewise, between 4 and 6, I have a test point at 5, and at 5 I have my derivative is 2, which is going to say that my derivative is always going to be positive between 4 and 6. Between 6 and 8, I could choose, let's say, 7. At 7, it's not so nice. Let's just assume that's like a negative 1.3. More importantly, it's negative between 6 and 8, and then a point right after 8 we could say is 9, and it looks like, I don't know, maybe my derivative there is going to be like a 1.9, which in this case is going to be positive. You're going to see that I have actually 3 intervals where my derivative is positive, which is going to tell me that my function, my initial function f, is going to be increasing on those intervals. So it's asking about where f is increasing. In this case, I'll identify that as increasing from, let's assume that I stopped right here. So I'm going to go from 0 up to 2. I'm going to increase from 4 to 6, and then I'm going to increase after 8, and let's just assume this goes on for the rest of time. So from 8 all the way up to positive infinity. On the other side of the coin, I'm going to have this conversation about where is this thing decreasing. That's going to be looking at where is my derivative negative. So I'm going to be decreasing on the intervals from 2 up to 4, as well as from 6 up to 8. So I have this nice kind of connection of looking at where I'm increasing or where I'm decreasing. Well, what I can do after that is I can easily use this information to identify my local maxes or my local mins. Well, if you look at 2, you're going to have that your function, your initial function f, was going to be increasing and then decreasing. At 4, you're going to have this conversation where it was decreasing and then increasing. At 6, I'm going to have increasing and then decreasing. and at 8 it's going to be decreasing and then increasing. So you can see that 2 of those points are going to be connected to minimum points, and 2 are going to be connected to maximum points. So I'll have local maxes, in this case, at x equals 2, and at x equals 6, and I will have local mins when x is equal to, in this case, 4, as well as when x is equal to 8. So it's the exact same stuff that we did earlier, except for in this case, I'm not having to test all of this stuff actually into a function. I can just simply use the graph of this derivative, which actually makes them kind of nice because they're a little bit quicker to do because you can just look at the graph and pick off numbers rather than to be kind of like, oh, I have to plug in 2/3 into this random derivative and then see if that's going to be a positive or a negative number. In this case, you can just look at the function, pick off, oh, it's actually positive, so I know I'm increasing at that stage. Okay, so next I'm going to look at this conversation of where is this thing actually going to have some interesting points kind of wrapped up in the conversation about my inflection as well as concavity. These things are all going to be connected to a conversation about my second derivative, which you can see my second derivative, which in this case is going to be the derivative of my first derivative, is going to be interesting when x is equal to 3. Because this tangent line here at 3 is going to be 0, that's going to say that my second derivative, because I'm differentiating my first derivative, is going to be 0 at 3. So this tells me that f double prime of 3 is going to be 0. So that's going to be a point that's going to be worth testing. Another point that might be worth testing is going to be at 6. I actually don't have that my second derivative exists at 6 because I don't have a first derivative that exists at 6. So I most certainly can't differentiate that thing again. So what I'm going to do is I'm going to create another one of these little tables of values. I'm going to have x values down here. I'm going to have my second derivative values here, and then I'm going to talk about what is the sign of that second derivative. The interesting point that I want to test is 3, and I know that my second derivative there is going to be a 0. At 6 is also going to be an interesting point, and my second derivative there does not exist. So I want to test some points around those things. In this case, let's go and test a point to the left of 3, and something that might be interesting is, I don't know, maybe like a 1. So I want to see what's happening in my second derivative at 1. Well, in this case, what I want to do is I want to see what is kind of more or less the tangent line's slope here. And if I kind of roughly sketch in a tangent line there, you can see that the slope of that thing is about -1/2. And in this case, because I'm differentiating my first derivative, the slopes here are exactly the values of my second derivative. So at 1, my second derivative is going to be a -1/2. More importantly, it's going to be negative. So it's negative, negative, negative from kind of 0 all the way up to 3. After 3, I want to test another point, and let's say maybe I do it at 4. If I draw another kind of rough tangent line in this case, you can see that my slope there is going to be a 1/2. So at 4, I'm going to have a second derivative being 1/2, which more importantly is going to be positive. At 6, that's where I don't have a kind of second derivative, so I want to test kind of what's happening there. Maybe I had one of these really weird cusp initially, and it switched concavity. But in this case, I'm actually going to see, I don't know, grab another point afterwards. If I take, let's say, 8. If I look at 8, maybe just kind of poorly draw another tangent line there, I'm just going to say that that slope's also 1/2. More importantly, I'm just caring about that slope being positive, which you can see happening as well. So I'm going to have one interval where my second derivative is going to be negative. That's going to happen from 0 up to 3, which is going to be that I'm going to be concave down from 0 up to 3. The other intervals where my thing is going to be a second derivative being positive, that's going to be where I'm concave up. So I'm concave up on the intervals from 3 to 6. I'm jumping over 6, and then I'm going all the way up to the rest of eternity. So I have this kind of weird break that's happening at 6 just because I know that my second derivative doesn't actually exist there, so I'm not going to use that kind of in consideration. So I'm going to hop over 6 and then continue on afterwards. You can see that at 3, I have this switch in concavity. I went from negative to positive, so I'm going to have an inflection point. Inflection point when x is equal to 3 in this case. So I get this nice switching point happening when x is equal to 3.